Hi everyone, welcome back. In this section we're going to look at double integrals over regions which are described in terms of polar coordinates. So let's look at a problem from Calculus 2 involving polar coordinates. That is, we'll find the area bounded by the cardioid r equals 1 plus cos theta. Let's first get a sketch of this region in the plane. So cardioid, sort of drawing an exaggerated version of it, but looks something like this. Looks like this sort of heart-shaped region. So that's r equals 1 plus cos theta. And we're interested in the area bounded by this curve. Now if we think back to Calculus 2, the area we would compute as the integral over the theta values that sweep out the region. So what are the theta values that sweep out the region? Well, we'll start at theta equals 0, and then we just imagine these theta values sweeping out the region. So that's theta going out to pi, and then beyond pi, all the way to 2 pi. So that's theta is pi, but also theta is 2 pi. So theta sweeps out the angles 0 to 2 pi. And then what is the integrand? Well, the integrand, as we found in Calculus 2, is 1/2 r squared d theta. Or in this case, since r is 1 plus cos theta, this is the integral of 1/2 1 plus cos theta squared d theta. Now I'm going to put this in a different color, this 1/2 r squared. So that was the result we learned in Calculus 2. We'll actually see how we can derive this result using the techniques we're going to learn in this section to do with Calculus 3 and double integrals. But before we get into that, let's just finish off this calculation. So how would we have calculated this in Calculus 2? Well, we would expand this out. I'll bring the half out front. I get a 1 plus a 2 cos theta plus cos squared theta d theta. Then we'd use the trig identity on that cos squared theta, because finding the antiderivative of cos squared theta is difficult. But if we use the trig identity, that cos squared theta is 1/2 plus 1/2 cos 2 theta, so that's the double angle identity. Then that's not so bad anymore. So the integrand becomes, so we got a 1 plus a half, so that's 3/2, and then we got times another half, so that's 3/4, and then we've got a 2 cos theta times a half, so that's a cos theta, and then we've got a 1/4, so plus 1/4 cos 2 theta d theta. So a little bit of work to rewrite the integrand in such a way that we can compute its antiderivative. So that would be 3/4 theta. The antiderivative of cosine is sine, so that's sine theta. The antiderivative of cos 2 theta is sine 2 theta with a half out front, so this is now a 1/8 sine 2 theta, and that's from 0 to 2 pi. So we get a 3/4 times 2 pi, or 3/2 pi, and then sine of 2 pi, sine of 4 pi, sine of 0, and sine of 0 are all 0, so this evaluates down to 3/2 pi. So it's the formula that I really wanted to draw your attention to in doing this example, because this is something we learned in Calculus 2. We learned that to integrate the region bounded by a polar curve, we integrate the function 1/2 of r squared. And we're going to see in this section that when we take a step up into higher dimensions and we look at volumes, integrals of volumes where the base is defined by a polar curve or a polar region, that specifying it to the case of areas will actually give this formula from a different perspective. So we're going to see how we can generate formulas from previous courses from the new tools we're learning in the current course. Now in order to do this, in order to get the ball rolling for multiple integrals over polar regions, We essentially do the same thing we did with rectangular regions. The idea is to set up an integral that represents the volume. How do we do that? Well, we chop it up into a bunch of little bits. Over each little bit, we approximate it with an object that we know the volume of. We sum up over all of those volumes, and then we let the number of those slices, the number of those pieces go to infinity, and we get the double integral that represents the volume. We're going to do the same thing here, but rather than chop it up into rectangular pieces, we are going to chop it up into the analog of a rectangle in polar coordinates, which we call a polar rectangle. So what is a polar rectangle? Well, just like a rectangle in Cartesian coordinates, a polar rectangle is going to be trapped between two constant theta values. So let's say theta is equal to alpha and theta is equal to beta. And it's also going to be trapped between two constant r values. So we'll say r is equal to a and r is equal to b. So there's our polar rectangle. It's like the crust of a slice of pizza, if you want to think of it that way. So there's our polar rectangle. What we'd like to do is figure out what the area is of a polar rectangle. Well, the first thing to recall, we know what the area is of a sector of a circle, or think of it like a pizza slice. If we know what r is, and we know the angle made, then the area is 1/2 r squared theta. So that's the area of this shape of pizza. And so what is the area of this crust-shaped region? Well, we can think of it as the area of the big slice minus the area of the small slice. The area of the big slice is 1/2 the radius of the big slice squared times the angle, and the angle is just beta minus alpha. Take away the area of the small slice, which is 1/2 a squared, beta minus alpha. So a little bit of simplification, we get 1/2 b squared minus a squared, beta minus alpha. We can factor that difference as squares. That becomes a 1/2 b plus a, b minus a, beta minus alpha. And what is b minus a? Well, b minus a is just the difference in the radius. So it's the radius of the big minus the radius of the small. What is beta minus alpha? That's basically just the angle that we have. So that is beta minus alpha, and this distance here is b minus a. What is 1/2 b plus a? Well, b plus a divided by 2 is just the average radius. So that's the average radius, which maybe I'll put it in a color here. So we've got this average radius. We'll call that r bar for the average radius. So this formula can simplify down to 1/2 b plus a, that's really just the average radius. B minus a, that's just the change in the radius. And b beta minus alpha, that's just the change in theta. So that's our area of this polar rectangle. Now what we're thinking about is when we take these regions in the plane and we slice them up into smaller and smaller and smaller polar rectangles and then sample the function at a point in that polar rectangle to get the height. We take the base area times the height for that slice, and then we add up over all of them, form the Riemann sum, let the number of those slices go to infinity, or let the length and the width of these slices, so in this case the delta r and the delta theta, go to 0, and that produces the double integral, which represents the volume. So what we are interested in is when these things are really small, when the delta r and the delta theta are close to 0. So that is when a is approximately equal to b which is some radius r, and when beta is approximately equal to alpha, what we have is that the area of that region, which we'll call dA, so the area element or the area of a really small polar rectangle, is basically r dr d theta. It's basically the radius of, or the distance this polar rectangle is from the origin, times the small differential, or the small change in radius, times the small differential, or the small change in theta. And so there is our small area, or what we call the polar area element. And it's this thing, that's the area of the little tiny polar rectangle, that we're going to multiply by the height of the function sampled at a point in that polar rectangle, and then we're going to integrate over all these. So we basically integrate the function times dA over the region. So that means that we get this result. If we want to find the integral of the function over the region R, then what we do is we just replace dA. So we put everything in terms of polar coordinates. The region gets expressed in terms of polar coordinates, the function gets expressed in terms of r and theta, and the only subtle part, the only part we had to do a little bit of thinking about is what happens to the area element. dA, well, in Cartesian coordinates that's dx dy, it's length times width. But in polar coordinates that's r dr d theta. So that's the only thing we had to think about. That becomes r dr d theta. And similarly, if we're doing this over a general region in polar coordinates, so a general region means that our theta value is trapped between alpha and beta, but our r value could be trapped between two functions, so that would look something like this, where theta is trapped between two angles, theta equals alpha, theta equals beta, and r is trapped between two functions. This is the region we're interested in. That inner function, or that small radius, is r is equal to h1 of theta. The outer one is r is equal to h2 of theta. So that's the region we're interested in, and that's how we set up the integral. The r value goes from h1 of theta to h2 of theta. We're thinking of it as like a slice that goes out like this, a line segment, and then we let that line segment sweep out all of these angles as the angle goes from alpha to beta. And the key thing is indicated there in yellow. The area element dA gets replaced with r dr d theta, and everything else gets written in terms of the polar coordinates. So let's have a look at an example. Find the volume of the solid that lies below the surface of z equals x squared plus y squared, so this is a paraboloid, and above the plane region R bounded by this polar curve. So this polar curve, R equals 2 cos theta, that defines a circle centered at 1 and of radius 1. So it defines a circle that looks like this. Now why, you may ask, how do I get that? One is you could do the techniques that we learned in Calculus 1 for sketching polar curves. You could sketch this polar curve as a Cartesian curve, so a horizontal theta axis, a vertical r axis, and then translate that into the polar axes, or the polar coordinate system. That's one way to do it. Alternatively, we could try to work just with the equation. And so I know that cos theta is x over r, so I could write this equation as r equals 2x over r. But then I can clear the denominators, get r squared is equal to 2x, or r squared is x squared plus y squared, that's equal to 2x. We can bring the 2x over as an x squared minus 2x plus y squared is equal to 0. We can complete the square, we get an x squared minus 1 plus y squared. So when I completed the square, I added a 1 on the left hand side, so I'll have to balance that by adding the 1 on the right. And that is a circle of radius 1 centered at 1, 0. So that's that circle that I drew. from the polar curve. If we didn't know that it was a circle like this, we could get it by working with the equation and writing it in its Cartesian form. So that's the region that we are interested in integrating over, and we want to integrate the corresponding function, x squared plus y squared. This region is best described in terms of polar coordinates because we've been given it in terms of polar coordinates. So what our double integral is over this region R of our function x squared plus y squared dA, when we express it in terms of polar coordinates, we are integrating over that region sketched above, x squared plus y squared, that we will write in terms of our polar coordinates, that would be r squared. dA is r dr d theta. What are our integration limits? Well, I've written my r variable first, so we can work out the r limits of integration. R would go, and in this case, I start at r equals the smallest value on the curve to r equals the biggest value. So r goes from 0 all the way out to the point on the curve. So it goes from 0 all the way out to 2 cos theta. And then what do the theta values have to do to sweep out the region? Well, I think about this theta equals 0. So that's theta equals 0. And then theta values sweep around to theta equals pi by 2, past pi by 2, all the way to theta equals pi. So that goes from 0 to pi. And so there is our integral that we want to compute. The integral from 0 to pi, the integral from 0 to 2 cos theta of r cubed dr d theta. So we can go ahead and work that out. The inner integral becomes 1/4 r to the 4th from 0 to 2 cos theta d theta. And then that becomes the integral from 0 to pi. The 2 cos theta gets plugged in for r. That becomes a 16 cos squared. Cancels with one of the quarters up front, so that becomes 4 cos squared theta d theta. Or in other words, it's 4 times the integral from 0 to pi of, oh, that's not a cos squared, that's a cos to the 4th. Sorry, cos to the 4th theta d theta. And then at this stage, we'd have to use techniques from Calculus 1. So it's a cos to the power of 4 theta. We can use some identities. We can start to reduce this, or we can use some of the reduction formulas. The idea is that there's a little bit of work to do here, but these are techniques that we learned in Calculus 2. So I will leave that for you to practice your Calculus 2 techniques for finding the integral of this, and just write down that our final result in this case is going to be 3 pi by 2. And so there's our final result. So again, the key point to this example was this is the integral we wanted to compute, and then we convert to polar coordinates. And in doing that conversion, we've got to convert our integrand that went from x squared plus y squared, that became an r squared. We had to convert our dA. dA became r dr d theta. And then we had to work with our limits of integration. What is r ranged between? What is theta ranged between to sweep out the region we are integrating over? All right, let's have a look at another example. Let's consider the double integral I, which is the double integral over this region of sine x squared plus y squared dx dy. First, let's sketch and describe the region of integration. So we'll go ahead and sketch that region. So we've got x. Sometimes in this case it'll help to write it out, maybe, to collect our thoughts. So x is going to range between y and the square root of pi minus y squared. And y is going to range over the values 0 to root pi by 2. So we've got y equals x as one of our boundary curves. We've also got x is equal to the square root of x squared minus y squared. Well, that probably more easily see what it is by just squaring both sides. X squared is pi minus y squared, or in other words, x squared plus y squared is equal to pi. So this becomes a circle of radius root pi. So that's r equals root pi. It's a circle of radius root pi. And then we've got the y values range between 0 and root pi by 2. In other words, the value up here, that's when our radius is root pi, or in other words, our y value is root pi by 2. And our corresponding x value of that point is also root pi by 2. So our domain that we're interested in, so the region we're interested in integrating over, is this region here. That's the region that satisfies all those inequalities. The line segment at y equals x, that could also be described as theta equals pi by 4. So now we've got this region described in terms of polar coordinates. This region is the r values range from 0 out to root pi, and the theta values range from 0 up to pi by 4. And the nice thing about this is a polar rectangle. Right? The r value is trapped between two constants, the theta value is trapped between two constants. Maybe that's worth putting an exclamation mark there. Polar rectangle. That means when we set up our integral in polar coordinates, we've got upper and lower limits of integration that are all constants. So nice things to integrate over, integrating over rectangles. In this case, the switch to polar coordinates gave us a polar rectangle to integrate over. So what is our integral? Our integral I, switching to polar coordinates, becomes the following. So our integrand becomes sine of x squared plus y squared. So maybe we should say switch to polar. So substitute x is r cos theta, y is r sine theta. So sine of x squared plus y squared, that becomes sine of r squared. dx dy, that becomes r dr d theta. And I'm going to move this r out front of the sine. Just shuffle those over, because when I see the r in front of the sine r squared, that immediately suggests substitution rule to do that integral. And what are our limits of r? Limits of integration on r are going to be 0 to root pi, and for theta it's 0 to pi by 4. So here's where we can also use the result that we had from the past. We've got an integral. The inner integral is an integral with respect to r, and its lower and upper limits of integration are constants. So that means that whole inner integral is constant relative to theta. So I can actually just split this integral up into the two integrals, the integral with respect to theta, and then the other integral with respect to r. So now we immediately see that once we've converted to polar coordinates, this problem just splits up into two calculus 2 integrals, two integrals of a single variable. So this first integral is pi by 4, and then the second integral becomes negative 1/2 cosine of r squared, and that's evaluated from 0 to root pi. So that becomes pi by 4 times negative 1/2 cos pi minus cos of 0. Cos of pi, that's negative 1. Cos of 0, that's 1. So we get negative 1 minus 1, that's negative 2, times negative 1/2, that's 1. So this works out to a value of pi by 4. Okay, so again, the main ideas in this example, not so much the evaluation of the integrals, not so much the techniques of evaluating integrals. Those are all just boiling down to Calculus 2 techniques. The main idea is getting that integral set up in the first place. So in this case, we had an integral that was expressed in terms of x and y's. We wanted to get it in terms of polar coordinates. And so the conversion to polar coordinates, getting our region sketched, reading off our limits of integration from that sketch, those were all the key elements in setting up this problem. Once we did that, then we use our Calculus 2 techniques to evaluate. So this ends the first part of the video on double integrals over polar regions. In the second part of the video, we'll look at some more aspects of doing this conversion, but in particular we'll look at a couple of cases where we evaluate functions of a single variable by reinterpreting it or reimagining it as living in higher dimensions or bringing in an extra dimension and using the techniques from Calculus 3. These ones we're just learning about changing coordinates into, or changing our Cartesian coordinates into polar coordinates, using these techniques to rewrite or redo integrals from Calculus 2. And so there'll be a couple of examples in the next video where we do this, where we exploit this new knowledge to help us attack problems from the previous course. All right, see you in the next video.